So, good morning. I am Krishna Kumar. We look at the final episode of this series of lectures on linear algebra. It ends with a consideration of certain examples on Jordan form, which will throw a lot of insight into what Jordan form is all about and how to actually compute the Jordan form and how they are intimately related to the uh, characteristic polynomial and the minimal polynomial. Okay, let us first look at this example. It gives some indication, or it clarifies that two operators need not be having the same Jordan form even if they have the same characteristic polynomial and the same minimal polynomial. So let us look at this example. It's a very interesting example. So let A be given by a 4 by 4 matrix which is of the form 2 1 2 1 0 0 then 0 2 a parameter A. Now consider A as an operator from R4 to R. That means A is taken as now we can easily check. I mean, it's very simple to work out the characteristic polynomial of A is minus 2 to the power 4. Observe that A is the direct sum of two 2 by 2 matrices. As you can see here, this one and this one. That's the structure of the matrix. Now, therefore, it's quite easy to see that the minimal polynomial now we consider the two cases, that is if A is equal to 0 or 1, A is already in the Now note that in both the cases, since the characteristic polynomial and the minimal polynomial do not depend on A, they are the same for both. Either case. But we shall observe that, so there are two forms in which it appears. See, so the two different forms are this: 2, 0, 1, 0. There is nothing that we need to do there. 0, 0, 0, 0, 0, 0, 0, 0. Then this is the case where A equal to 0, or the other one is, this is when A equal to 0. A equal to 1. This is 2, 0, 1, 2. And a repetition of the same thing, 2, 0, 1, 2. Both credible Jordan forms. These are the two cases that we have. But all that you observe is that when A equal to 0, the null space of I is 3-dimensional. Now when A equal to 1, the null space of A minus 2i is 2-dimensional. Therefore, the two operators are essentially different. Structurally, what is the inference that you make? Hence we conclude that two operators having the same characteristic polynomial and the minimal polynomial is structural way to say. That is, they may not be similar. Now this is one of the inferences that we make out of this particular example. Is some insight into the structure of operators. So just by verifying that the characteristic polynomial and the minimal polynomial are the same does not imply these operators are similar. So we come to another fascinating example. Now this has something to do with the differential equations. So the next example. This is something to do with the linear homogeneous ordinary differential equations and their solutions. Now what we recall is that if you have an nth order linear homogeneous ordinary differential equation, then the solution space is a vector space of dimension n. That is something that we recall. So consider the nth order linear homogeneous differential equation. Equal to 0. Denote this by 1, where AI is complex numbers. Then the characteristic polynomial of the above equation given by f lambda equal to lambda to the power n plus E naught and see, when you try to work out the solution of this equation, you write down the corresponding auxiliary equation f lambda equal to 0 and then find the roots of that or factorize it. And you know that since we are working with C, it factors, and we have f factors into the following form. It's f lambda equal to lambda minus lambda 1 to the power r1 where of course 1 less than or equal to Ri or Ri is greater than or equal to 1. They are integers and positive integers, and R1 plus equal to n. We take, these are the distinct, and we have lambda I different from lambda j whenever I is different from j. Now these are the conditions. So these are all distinct zeros of the characteristic polynomial or the auxiliary equation. So lambda 1, lambda 2, etc., lambda k are the distinct zeros of f. Now from the general theory of ODE, the solutions of one form a vector space of dimension n, where n is the order of the differential equation. I mean, it's a beautiful theorem. Okay, just links up the theory of linear equations essentially to linear algebra, and a lot of nice results from linear algebra become very handy in finding out the solutions of this. So that's something very fascinating. And we can even, because these are constant coefficients, we can even write down a ordered basis for this space. So if I list them out, now let me write down Bi. I define as e to the power lambda I x x e to the power x to the power Ri minus 1 e to the power. These functions are solutions of this equation. Okay. Now you see that these functions satisfy this particular differential equation. That's quite easy to. This comes from the fact that you see you have this one, namely that lambda minus, or if we, I think maybe it's worthwhile to recall and connect everything together. If you look at this collection of vectors, now you see that so for this is true for I, this is Vi. Now it's quite easy to see the following, that they are solutions of the equation. So if we set D dx, then the set of functions in Vi are of solutions of and you see that FD is essentially, since FD is not right here, right? RK these are solutions of equation 1. One given by zero. Now, how many such solutions are there? So, if you set V equal to this gives an ordered ordered basis for the solution space of now this is something that we know from differential equation. So we explicitly know what a basis for this is, provided of course you can factorize successfully the polynomial f lambda. Okay, see that here lambda 1 is of multiplicity r1 or algebraic multiplicity r1, etc. Lambda k is of algebraic multiplicity rk. So now we go in a different direction. Now we are going to link these facts with the Jordan form of the operator D acting over the solution space. So let on F, I'll put some other equation. Okay, put Y here. Y, which is n times continuously differentiable functions, with the property that uh, zero. Then dimension of V this we know. Now observe that D maps V into V, or D belongs to, is a linear transformation. Now the question that you are asking is this: what is the Jordan form of something very interesting question. What is the Jordan form of D? Now this is the question that we are trying to look at. So let us analyze this. So what is the usual procedure? The usual procedure is, first find out what is the characteristic polynomial for D. Okay. Find the minimal polynomial. Once you resolve these two, and then also break up the vector space using the primary decomposition theorem, we can write down the Jordan. So this is the procedure. So let us work it. It's interesting. Very fascinating, right? Now how do we proceed? Now D is from V into V. So what is the characteristic polynomial of? We first observe that the characteristic polynomial of D is f lambda. Why? Because you see that on V, f of D equal to 0. And degree of and we also know that f is monic. So all these things put together, it follows that this is the characteristic polynomial. Okay. Now so f lambda is the characteristic polynomial is now f lambda is given by as we have seen. So the question that you ask is this, that is the characteristic. What is the minimal polynomial? Now we see that the minimal polynomial p lambda has to be something of the form something like n1 here r1 plus rk equal to n, where you have 1 less than or equal to ni less than or equal to ri, and it need not be equal. Okay, but certainly it is. That means all the factors they have the same factors. Both p and lambda have the same factors, and the degree of p is in general less than or equal to the degree of f. But we prove that this is essentially p is equal to, so what we claim is that is the minimal polynomial is the characteristic polynomial. That means each ni is equal to ri. Now let us prove this. If p is not equal to f, then there exists some j such that nk is nj is strictly less than now consider the vector. Consider the function x to the power minus 1 x, which of course is an element of p, because we have already said that this is a solution of this PD equal to 0. Okay. Now we observe that d minus lambda j to the power I nj operating over x to the power rj minus 1 e to the power lambda j x is not equal to 0. Here we use the fact that nj is strictly less than. But this is quite easy to work out, because, and that implies PD of not equal to 0. Okay, what is the implication? The implication is that the okay, that of course it shows that this video, it implies that E is not a minimal point, because PD is not equal to 0. That's the reason. Therefore, P is not a minimal polynomial. What does it mean? It implies P equal to F, or the characteristic polynomial and the minimal polynomial are and identical. Okay, so that gives some information. Okay. So you have a, now what one does is, we now look at the breakup of the, we apply the primary decomposition here. Okay, right? So let us define the following. So we work on the we apply the primary decomposition theorem. So define, so we have P lambda equal to and then define Vi as the null space of D minus lambda I for I equal to then we have the following. Then V equal to and dimension of Ri and so this is the primary decomposition of the space V with reference to our operator D. Okay. Now what we have is the minimal polynomial of D restricted to Vi is lambda minus lambda I to the power R. If you want to call it, you call it Pi. Okay. Now we define what are called the nilpotent operators associated with the D. Okay. So define Pi. Then Ni is nilpotent. The reason is that you have lambda minus lambda I to the power Ri equal to 0, or the characteristic polynomial and the minimal polynomial. For Ni, lambda to the power Ri R. Because since zero, And of course, you can also show that now this is also the minimal polynomial, because this is so because ni to the power ri minus 1 operating over x to the power is equal to this. If you compute, this is equal to ri minus 1 factorial times e to the power lambda ix, which is not equal to 0. Okay. The of and the characteristic polynomial of ni are the same. So now what do we do? We write down the rational form of, so we write down the rational form for each what is called ni, and using that we write down the Jordan form for you can immediately write down the Nash what is called the rational form for ni. So let us write down. So we can write down the rational form. The rational form for is then the following matrix. Now what matrix is it? Is then given by And the Jordan form, this is a Ri cross Ri D restricted to Vi is then given by equal to which is equal to along the diagonal lambda I and then this way. This is true for I okay, which now combining these Jordan forms for AIs, we have the Jordan form for is the matrix splitting into K blocks and given by so you have got A1 here, A2 here, AK here, and elsewhere it is 0 here, 0 elsewhere. Now this is the corresponding Jordan form for the this is the Jordan form for the operator D. Okay, that's a very interesting connection between the nth order linear differential equations and the Jordan form of the operator. Now we take up few more examples to get some insight into the what is called the Jordan forms. Next example. Let A be a. It's a very specific example which will give some visibility into the working. Pi by pi matrix with characteristic polynomial F and a minimal polynomial whole square. Now let us take V to be equal to R5 or C5 because all the roots are here. Okay, then see A belongs to L. Now we write down the Jordan form for A. Okay, so we proceed as follows. What is V1? V1 is defined as the null space of A minus 2I whole square, and V2 defined as null space of A plus 7I dimension of V1 equal to 3, which is the algebraic multiplicity of lambda minus 2. It's the algebraic multiplicity of 2 in the characteristic polynomial, and dimension of and we have V equal to V1 plus V2. Now we take A AI. We observe that minimal polynomial for A1 is lambda minus 2 whole square. Okay, but the characteristic polynomial is therefore we can now write down the Jordan form. Okay, that's quite easy to write down. J1 say, we write this Jordan form, you will go through the same exercise that we did for writing down the Jordan form in earlier cases. But what we have is now, you see, you have the Jordan form actually goes into two blocks. Okay. The Jordan form has two blocks. One block corresponding to the minimal polynomial. Okay. So the Jordan form has the following blocks. Is a 3 by 3 matrix having two blocks. Given by what is it? This is equal to 2, 0, 1, 2, and you have 2 here. This is the J1. This is J1. Because if you work out the n1 has, see, n1 has the form. This is n1. See, this is the n1. Okay. Associated with this, which is given by a restriction of a to v1 minus 2i. Okay, so that's what you have. This is the corresponding n1. Therefore, this is the Jordan. And for A2 is the 2 by 2 matrix because you see that in the case of n2, what happens? What is the characteristic polynomial? The characteristic polynomial is x square or lambda square, and so also the uh, minimal polynomial. So they are the same. Therefore, the structure of J2 is given by this one. This is equal to -7, 0, 1, -7. So here N2 is given by 0 because the characteristic polynomial lambda square. That is the reason for it. Therefore, the Jordan form of is given by J J1 is a 3 by 3 matrix and this is a 2 by 2 matrix. So that's how it comes. Okay, right? Now we shall look at this problem in a more general context, but still with a specific structure for the characteristic polynomial. See, in this forming the Jordan form or writing down the rational form for the nilpotent operators is the important part. So once you write that, it comes immediately. So here there is only one rational form for N2. Okay. That is because the characteristic polynomial and the minimal polynomials are the same. Here there are two blocks in the rational form for N1. Okay. One corresponding to the minimal polynomial, say P1 or something like that, which is lambda to the power 2, and then the characteristic polynomial is lambda to the power 3, so there is another factor coming for lambda. Okay, so that's how it comes up. Now let us see, next problem is very interesting. We shall investigate the number of we shall look at the number of Jordan forms with characteristic polynomial Okay, this, you know that the minimal polynomial of the operator plays a significant role in determining the uh, Jordan, that we know already. Therefore, let us look at all possible situations that can arise in this case. It's very interesting. Okay, what are the different minimal polynomials which are related to the characteristic polynomial f? This is the question that you have. Okay, so let us take this. Okay, there are different forms in which it can arise. So this is the question that you are asking. Let us list them out. Okay, we will list them out. So P1 minus 1. Second one is P2 lambda plus 2 whole square. Third one is then the fourth one is P4 lambda now you see that in all these cases that Pi divides F. Okay, these are 4 different types of this, and now there are more. Fifth one is so all these possibilities do exist. Okay, therefore the operator has the corresponding Jordan form dictated by the various minimal polynomials, because the characteristic polynomial is given by this. The minimal polynomial divides the characteristic polynomial. So these are the only possibilities that you can have. Okay, let us now analyze this one by one. It's interesting. It's very, very fascinating. Once again, you see that the possible eigenvectors or the characteristic values are lambda equal to -2 and lambda equal to 1. So the characteristic values are -2 and 1 of multiplicity 4 and 2 therefore the Jordan form is a split into two boxes. Two blocks. See, what you have is this. Suppose let us take V to be equal to R6. Then we take N to be what is called the null space of, okay. So we have V1 defined as the null space of what you call T minus, okay, T belonging to T minus, what is it? To the power, yeah, so that differs some R and V2 null space of T minus I S R plus S equal to 6. Now R so these are the possible. Now you see the dimension of V2 equal to, because the T varies in different circumstances. So once you fix T, one of this possibility is fixed. Okay. So here we are, T is generic in the sense that it can accommodate any one of these possibilities. Now let us take various situations. So let us analyze the first one. P equal to P1. Then P1 lambda equal to now you see that this dimension of E1 equal to 4, dimension of E2 equal to 2 anyway. Okay, right. But what happens in this case? Suppose you designate by okay. Suppose you designate by A1 restriction of A1 restricted to A11. A1 restricted to T1 restricted to what is called P1. Now let us write down the Jordan form for this. Then what you have? You have essentially, see, this is the one that defines it. Okay, now you see that P1 defines this. So what you have is that if you look at N11, P1 plus this is equal to then what you have is this is the nilpotent operator associated with A11 and this there is a nilpotent operator associated with N21. Okay, and then we can break it up. So what is the Jordan form? So likewise you have got N21 equal to A minus then you have got N11 to the power 1 equal to 0 equal to 0. Therefore, the corresponding J11 is going to be equal to equal to or what is called the Jordan form for which is the Jordan form for A1. Okay, Jordan form for T1 is given by then into two blocks. Only this is here. This is it. Because you see the polynomial for on V1, the polynomial for N1 is a lambda to the power these are the minimal polynomials. That's it. Now let us take the second example. I leave that as it is, or I can even use this piece. Let us work with the second one. Second one is we will write T2. T2 with the minimal polynomial T2. And which is equal to P2 lambda equal to lambda plus 1 lambda minus 1. Therefore, you see that you have again breakup V1 equal to what is it, null space of T2 plus 2I whole square and V2 equal to null space of T2 plus T2 minus I. So V equal to 2. And again you have got T2 restricted to V1, T2, suppose this is denoted by A, we have used 1 1, 2 1, okay, 2 1 and A Q. Then you see that the characteristic polynomial or the minimal polynomial for A21 is whole square equal to lambda minus 1 that is that. Now what are the possibilities that can occur here? Here you see there are, see if you look at the minimal polynomial for n1, okay, so we write then you see that the minimal polynomial, these are the nilpotent operators. Minimal polynomial for a n lambda square. Minimal polynomial for n22 is the lambda. That means you have 0, 0. These are the operators that you have. Then you have got the corresponding Jordan form for, or what you call the rational form for n21 and n22 are there are two different possibilities that can come, because you see that the characteristic polynomial for n21 equal to lambda to the power 4. Therefore, we have three blocks. I mean, there are two possibilities. Possible for what are they? They are corresponding to what you call, one is, I will write down the minimal polynomial for this, corresponding to the following breakup. You have got lambda square, lambda square, these are the one possibility, or corresponding to lambda square, lambda, lambda. So see, they are the when you write down the rational form, You have got the corresponding minimal polynomial for the cyclic decomposition. You are writing down the cyclic decomposition. So these are the minimal polynomials associated with the blocks. Okay. So corresponding to each one you have a representation. So that gives, so I take out this. Therefore, there are two Jordan forms possible. The you have got J1 for this associated with lambda square is so on. It's a 4 by 4 matrix that you have 0, 0, 1, 0. This is J2. And similarly, and J21 tilde associated with is, it will go into 3 blocks. One is this 0, 0, 1, 0, 1 block, 0. Okay, this is J2. And J22, there is only one possibility. It's given by okay. Therefore, the corresponding J2 J2 has two possible forms. See, it has sort of, so this is going to be 1, 1, 0. This is the form. No, sorry. This one corresponding to J21. Then you have okay, J22 is essentially corresponding to, so this is this. And here you have the following breakup. The first one corresponds to this one. So this is going to be minus 2, minus 2, 1, 0, 0, and you have minus 2, minus 2, 0, 1. This is the form. Now J2, let me call this J2 tilde. This is equal to, this is another form that is possible. This is given by J2 tilde is of the following form, namely this is corresponding to J21 tilde, and here of course it is the same. What you have is this 1, 0, 1, this breakup. Then here you have the breakup given by then you have here, of course what you have is this z minus 2, 0, 1, minus 2. This is the so there are two Jordan forms possible associated with this. One Jordan form here, two Jordan forms here. Now you can write down the third one. I will write down the third one and the fourth one, and then this is the only part. So you know what is the Jordan form associated with lambda plus 2, lambda plus 2 whole square. Lambda plus 2 whole square, there are two different forms coming. Lambda plus 2 whole cube, there are three. There is only one form coming, and there is only one form coming. So let us write down that. Write down the next one. So I will just give you the list this out, then it will be clear to you what are the Jordan forms. Work with T3 now. Oh, this is okay. Let me list out the cases for 3 associated with the T3 having minimal polynomial P3. Okay, the form is this. J3 is then taking up the form. See, it has got two blocks again. One a 4x4 block and a 2x2 block. And this is equal to minus 2, minus 2, minus 2, 2 here, and you have 1, 1, 0, 0, 0, 0 here. And in this case, of course, whatever we had been getting, namely that this is equal to 1, 0, 0, 1, this one. In the fourth case, we have T4 having the minimal polynomial T4 is simple. It just comes out to be this. This is a major breakup you have. Now here it is going to be minus 2, minus 2, minus 2, minus 2, 1, this is the form, and of course here it is 1, this is the form. Now for T5, whole square. So this is going to be minus 2, minus 2, minus 2, minus 2. And here it is going to be 1, 0, 1, 1, 1. That's easy to solve. That's about T4. In T5 we have analyzed. Now we go to T6. For T6, this is T6 with minimum polynomial. With the minimum polynomial, see here there are two forms available. What is one is J6 given by, as we have seen earlier, two forms available. 0. This is corresponding to this part. This part you have the following forms: minus 2, minus 2, Then you have got minus 2, 0, 0, minus 2, or 1 minus 2. This is one form. And J6 tilde will be something like this, that you have got again this breakup. So here it is 1, 0, 0, 1, 1, 0, 0. But this part is going to break up into 3 matrices. So it is going to be minus 2, 0, 1, minus 2, minus 2, minus 2. That is J6. Now the others are fairly simple, straightforward. J7 and J8, and probably I will stop. So there are two possible forms available here. That is because you get x minus 2 whole square, and the companions that can go with it is x minus 2 whole square, x minus 2 and x minus 2, and x minus 2 whole square with x minus 2 whole square. So 7, you take T7 with lambda J7 takes this form. And here you have one, 0, 1, 1. This is for this. Now 8th one, T8 with minimal polynomial lambda plus 2 to the power 4 into lambda minus 1 whole square. And that gives J8 here of course 1, 0, 1, 1. And here what you have is the following scenario, namely get minus 2, minus 2, minus 2, minus 2. So you have got 1, 1, 1, and 0 here. So this is what you get. So J8 is this. Now this is the breakup that you have. All possible what is called Jordan forms that are dictated by the characteristic polynomial lambda plus 2 whole square into lambda minus 1 whole square. Okay, thank you very much. Stop here. So that concludes our analysis for the time being of linear algebra. There are a few more topics worthy of discussion. I will come back with them later. One is, of course, giving a structural definition of determinants, which needs the study of what are called multilinear forms. The other one is again bilinear forms and the geometry associated with the bilinear forms. Now these are two things that we would like to look at. Apart from that, we would now, as a prelude to doing functional analysis, we want to look at finite dimensional inner product spaces. But these things I will do separately. Okay. So thank you very much. This wonderful journey I had, starting from the definition of linear spaces somewhere in Devgiri College, and now taken all the way up to this Jordan form. It has been a very, very, very satisfying work as far as I am concerned. And I hope you also enjoy it, and I hope these lectures help you to learn the essentials of a linear algebra program. Thank you very much.